Hi everybody, welcome back to College Algebra. Today we're in section R.5, still going through some of the prerequisite material that you'll need to understand and know before you move into the regular college algebra curriculum. So today we're going to be talking about rational expressions, and I'm going to show you how to put a rational expression in lowest terms. It's a lot like simplifying a fraction. And I'm also going to show you how to multiply and divide rational expressions, and then finally how to add and subtract rational expressions. So here we go. Now a rational expression is just a fraction that contains a variable in the denominator. And so here are a couple of examples of rational expressions. X squared minus 25 all over x plus 3 is considered a rational expression because you see it has this variable in the denominator. Also, the expression 4 over x would be considered a rational expression because it has a variable in the denominator. Now, you already know that the denominator of a fraction cannot be 0 because if the denominator is equal to 0, the fraction is undefined. The denominator of a fraction cannot be 0 because then you're dividing by 0, and that is undefined. Therefore, when you're working with rational expressions, the variable in the denominator cannot be allowed to be equal to any value that would cause the denominator to equal 0. Now, the domain of a rational expression is just the set of all values that the variable is allowed to have. The domain is just the values of the variable that are okay to plug in. If a variable is not allowed to equal a given value, then we say that that value must be excluded from the domain. In other words, that value must be left out of the domain. So just to give you the bottom line here, we can't let the variable be equal to any values that cause the denominator to equal 0. So any values that cause the denominator to equal 0 are going to be excluded from the domain. So let's take a look at example 1 together. And this example says, find the domain of the rational expression x plus 6 times x plus 5 all over x plus 2 times x plus 4. Now we know that the denominator cannot be allowed to equal 0. And we also know that any number times 0 is 0. So if either one of these parentheses adds up to 0, it's going to cause the denominator to equal 0, and that's going to cause the expression as a whole to be undefined because you know division by 0 is not defined. So we have to ask ourselves, what would cause this first parentheses to equal 0? Well, if x plus 2 equals 0, that means that x is going to have to be negative 2. Because you remember to solve this, you would just subtract 2 from both sides. So you can see that if x were negative 2, this parentheses would add up to 0, and this parentheses would add up to 2, but 0 times 2 would still be 0. So we can't let x equal negative 2. And if x plus 4 equals 0, that means subtracting 4 from both sides, that means x equals negative 4. So we can't let x equal negative 4 either, because if we do that, then this parentheses will add up to 0, and then 0 times whatever we have here will still be 0. So the two values that would cause the denominator to equal 0 are negative 2 and negative 4, and therefore negative 2 and negative 4 must be excluded from the domain. That is, we can't let x equal either one of those numbers. And so another way to say that is that the domain includes all real numbers except negative 2 and negative 4. Now this is how we would write it in set builder notation, which is a kind of shorthand way to describe a set of numbers. We would say that the domain includes the set of all values of x such that x is not equal to negative 2 or negative 4, and then close the curly braces. So notice that the curly braces make us say the set of, and then we give the name of the variable, the set of all x values, and then the vertical bar is read such that. So again, this says the set of all x values such that x is not equal to negative 2 or negative 4. And that describes perfectly what we found up here. Now here's a practice problem for you to work on. This one says find the domain of the rational expression, and you see that we have a very similar expression here to the one that was in the last example. And remember, to find the domain of a rational expression, we just have to leave out any values of x that would cause a denominator to equal 0. So that means we can't let the factors of the denominator equal 0. So that means that x minus 1 cannot equal 0, and that means that x cannot equal 1. And we also know that x plus 5 cannot equal 0, and that means that x cannot equal negative 5. So the domain is all numbers except these two. The domain is all real numbers except 1 and negative 5. So in set builder notation, we would say that the domain is the set of all x values such that x is not equal to 1 or negative 5. And that's it. Now let's talk about how to put a rational expression in lowest terms, or in other words, how to simplify a rational expression. So a rational expression is written in lowest terms when the GCF of the numerator and the denominator is 1. In other words, just like any other fraction, a rational expression is in lowest terms when the top and the bottom don't share any factors besides 1. So to simplify a rational expression, what you're going to do is factor both the numerator and the denominator, and then cross out any factors that appear in both top and bottom. And I know that we say we cancel those factors. Really, cancel is not a good algebra word, but you know what we mean when we say cancel, so I'm probably going to go ahead and say it. Now remember that you cannot cancel terms, we can only cancel factors. The difference between terms and factors is that factors are multiplied together, where terms are added together. So remember, we can't cancel terms, only factors. So for example, let's look at the rational expression 3x minus 6 all over x squared plus x minus 6. A mistake that a lot of people make is they try to cancel out the x's, and then they probably would try to also cancel out the minus 6's. And they would get 3 over x squared, and that is completely wrong. And the problem is that this x is not a factor of the top. It's a factor of the first term. And this x is not a factor of the bottom. It's just the middle term. These negative 6's are not factors, they are terms, and so they're not free to cancel. In order to simplify an expression like this, what we would need to do is say, we notice that there is a GCF in the top. Both terms in the top can be divided by 3. So we will factor out the 3, and that will leave us with 3 times x minus 2 for the top. And then the denominator is a trinomial, so we should try to separate that into two binomials. So first times first is x squared, and that means I'm going to have x times x here. Now the last term is negative, so that tells me these signs must be different. And 6 could be 3 times 2 or 1 times 6. I'm going to use 3 times 2 because that way I can get the middle term to add up to positive 1x. Okay, now that it's in factored form, notice it's 3 times x minus 2 and x plus 3 times x minus 2. So this is all factored. Notice that we have a common factor of x minus 2 in both top and bottom. So that's going to divide out, or cancel out is what we usually say. And the reason that happens is that anything divided by itself is 1. So multiplying by x minus 2 and then dividing by x minus 2 is really not having any effect on the overall value of the expression. So we may as well do away with those. And that's going to leave us with 3 over x plus 3. Now I know some of you are going to see the 3's here, and you're going to be tempted to cancel those out. But remember, this 3 in the denominator is not a factor of the denominator. This 3 is a term, so it is not available for canceling, and this is as simplified as this expression will get. Now let's practice simplifying a little more. Here we have example 2, and the instructions say write each rational expression in lowest terms. So we know that we can't cancel from terms, we must cancel from factors. So we're going to try to factor the top. Now I look at the 3 terms in the top, I see that that's a trinomial, And I also noticed that there's nothing that goes into all three terms, so I know I'm going to be able to break this trinomial down into two binomials. First times first gave us 2x squared, so that must be 2x times 1x here. Last times last gave us a negative number, so that tells me that the signs here and here must be different. I don't know right now whether the plus goes here or here. I just know that the signs have to be different. So last times last is 4. So my choices for 4 are either 2 times 2 or 1 times 4. Now notice that if I think about 2 times 2, I would have a 2 here and a 2 here, and that would create a GCF. But I'm not supposed to have a GCF in my expression. So I know that I'm going to have to go with 1 and 4, and I'm going to have to put the 1 here and the 4 here. Right, now let's see if this works, because if it works, outer plus inner should add up to positive 7x. So outer times outer is negative 8x, inner times inner is positive 1x. You can see that's going to add up to negative 7x, but I wanted positive 7x. So the good news is that I've got all the terms in the right places. All we have to do is change the signs. So now you can see that outer plus inner will add up to positive 7x. Now for the denominator, this is not a trinomial, so it's not going to separate into two binomials. But what I can do is factor a GCF from these two terms. So notice that 5 goes into both coefficients, and notice that x is common to both terms. So if I factor out a 5x, then I'm going to have two terms inside the parentheses. 5x times x would make 5x squared, and 5x times 4 would make 20x. So now you can see that everything is factored, and you can see that we have an x plus 4 in both top and bottom, so those will drop out. And our final simplified expression is going to be 2x minus 1 over 5x. And no further simplifying is possible because this x is not a factor of the numerator, so I can't use this x to cancel this one. Now in part B, I'm going to show you a little extra trick. Notice that here we have 6 minus 3x all over x squared minus 4. And the top definitely has a GCF of 3. So let's go ahead and factor a 3 from these two terms, and that's going to give us 2 minus x in the parentheses. The bottom is a difference of squares. X squared minus 4 is going to factor into x minus 2 times x plus 2. Now look at the two factors that we have here. In the top I have 2 minus x, and in the bottom I have x minus 2. These are very similar, but they are not exactly the same. In fact, they are opposites. In this first one we have a positive 2 and a negative x. In the second one we have a positive x and a negative 2. So no matter what you plug in for x, the value in the top is going to be the opposite of the value in the bottom. So what we want to do in a case like this is factor a negative 1 from one of the factors. It doesn't matter which one. But let's factor a negative 1 from the top. Now when I do that, that negative is going to come out front, and everything in the parentheses is going to change sign. So when I rewrite this, now I've got a negative 3 as my GCF, and because I have a negative out here, this is now going to be negative 2 and positive x. You see how factoring out a negative just changes the signs of what was inside the parentheses. Nothing in the denominator has changed. Now notice that the factor in the top still doesn't look like the factor in the bottom, but they are the same value now because in the top I have negative 2, in the bottom I have negative 2. In the top I have positive x, in the bottom I have positive x. So these are not written the same, but they are the same. I'm going to go ahead and use the commutative property to change the order of the two terms here. And so the only thing that will change here is that I'm writing negative 2 plus x as x minus 2. And then the denominator stays exactly the same. And when you write it in that form, you can see that the x minus 2's are going to cancel. And that's going to leave us with a final answer of negative 3 over x plus 2. Now that you know how to simplify, we can talk about multiplying and dividing. Multiplication is very similar to simplifying. In fact, you're not going to feel like you're multiplying at all. I know when I say multiplication, you start to think of the process we use to multiply things like distributing and combining like terms, but that's not what we're going to be doing here. When we multiply rational expressions, what we actually do is just factor all the numerators and denominators and then cross out any factors that appear in both numerator and denominator. Doesn't that sound exactly like what we did when we simplified? The difference is that here we'll have two rational expressions to work with instead of just one, but we treat them the same. Now, it's customary to multiply any remaining monomials back together, but it is not required for you to multiply polynomials back together. So you won't be going through any distributing or FOIL processes here. Let's take a look at example 3a, and we're going to be just multiplying here. And in part A, we have just a really simple example. I have 2y squared over 9 times 27 over 8y to the 5th. So now what I want you to do is get in the habit of simplifying before you multiply. See, if you multiply first, you'd have to do 2 times 27 and 9 times 8, and that would lead you to some pretty big numbers. But what you need to do is notice that 27 and 9 can both be divided by the same number, and that number is 9. So I'm going to go ahead and cross these two out because I'm about to divide them both by the same number. 27 divided by 9 is 3, and 9 divided by 9 is 1. Also, before we go forward, let's notice that 2 and 8 can also both be divided by the same number. 2 and 8 can both be divided by 2. So we'll go ahead and cross those two out, and 2 divided by 2 is 1, and 8 divided by 2 is 4. And now let's just kind of regroup and see where we are. In the top, we have 1 times y squared times 3. So that's going to be 3y squared. And in the bottom, we have 1 times 4 times y to the 5th. So that's 4y to the 5th. Now, we can do a little more simplifying with y squared over y to the 5th. And I know we just went over our exponent rules not too long ago, so you probably remember, but let me just remind you up here. If you have y squared over y to the 5th, that's like having y times y in the top and y times y times y times y times y in the bottom. Now, notice that each y in the top would cancel one of the y's from the bottom, and what you'd be left with is 1 over y to the 3rd. Now, let me make this easy for you. What you can do, instead of writing it all out like this, from now on, I want you to say wherever the larger exponent is, do the larger one minus the smaller one, and then put the leftovers where the larger exponent was, because you can see that's where the leftovers are going to end up. Okay, so down here, the 3 and the 4 will not simplify any further, but we know that 5 minus 2 is 3, so this is going to simplify to 3 over 4y to the 3rd. And let's look at part B. Now, before we can see what's going to cancel out here, we'll need to factor both of these trinomials. So I'm going to go ahead and factor the top left, 3m squared minus 2m minus 8. That is a trinomial. It does not have a GCF, so it's going to factor into two binomials. So 3m squared is going to be 3m times 1m, and the last term is a negative, so that's going to become a minus and a plus, or however you want to set the signs down is fine, just as long as you make different signs here. And now notice that our last term is 8. So my first thought is maybe 4 times 2. You can't know at first which way to put the numbers in there. You just have to stick them in there and see if they give you the right middle term. So outer times outer is going to be positive 6m. Inner times inner is going to be negative 4m. That's going to add up to positive 2m. So it's good that we got the 2, but now my sign is wrong, so I'll need to erase the signs and switch those. Now moving on to the denominator, again we have a trinomial with no GCF, so that's going to make two binomials. 3m squared is going to be 3m times 1m again. Last times last made a positive number, so that tells me these signs should be the same, and they should both be the same as the middle term, so they both need to be plus. and then last times last has got to be 8 again, but this time we want the middle term to add up to 14m. So I'm going to stick the 4 and the 2 in there, and let's see what we get for the middle term. Outer times outer is 6m, inner times inner is 4m. 6m plus 4m is 10m, not the 14 that we need. So let's try switching these two numbers, and let's see if that helps. This time outer times outer is 12m, inner times inner is 2m. 12m plus 2m is 14m, that's what we wanted. So this factoring is correct. Now look at the 3m plus 2. That is just a binomial, but it is not anything we can factor, so that goes there. 3m plus 4 stays as it is as well. And now let's see if we can simplify any of this. So here I notice that I have a 3m plus 4 in the top and a 3m plus 4 in the denominator, so we'll cancel those out. Also, we have a 3m plus 2 in the top and a 3m plus 2 in the denominator, so we'll cancel those out. And all that's left is m minus 2 over m plus 4. And again, I know it's a big temptation to want to cancel out these m's, but you cannot do it because these m's are not factors, they are terms, and they will not cancel. Now let's talk about dividing. Dividing rational expressions works exactly the same as dividing regular fractions. Instead of actually learning a new process for dividing, what we always do is we just restate each division problem in a multiplication form. And you'll remember doing this with regular fractions. So remember, the definition of division is to multiply by the reciprocal. The definition of division is to multiply by the reciprocal. Therefore, to convert a division problem into a multiplication problem, what you do is you leave the first fraction unchanged, and then you change the division symbol to multiplication, and then you flip the second expression over so that you have a reciprocal of that second expression. Let's practice here, and notice that the instructions say divide, and you see the divide symbol here. So what we're about to do is not necessary when you start with a multiplication problem. What we're about to do is take this division problem and convert it to multiplication so we can work it the same way we worked the last two examples. So here we have 15p to the third over 9p squared divided by 6p over 10p squared. So the first thing we want to do is write this problem in multiplication form. So we leave the first fraction unchanged, we change the divide to a times, and we flip over the second fraction, so it becomes 10p squared over 6p. Now it is very important that if you change one thing, that you change both. So if you flip, you must change divide to times. If you change divide to times, you must flip that second fraction. You can't change only one thing without creating a totally new problem. But basically these two expressions say the same thing. It's just one says it in division form and one says it in multiplication form. And now we can simplify this according to what we learned about multiplication. What we need to do is just divide out any common factors. Now I'm looking at the numbers that I have, and I have 15 and 10 and 6 and 9. And I notice that 15 and 9 can both be divided by 3, but 15 and 6 could also both be divided by 3. So I could do it either way, but notice that if I use the 15 and the 9 together, then I can use the 10 and the 6 together because both of these can be divided by 2. But if I divide out the 3 with the 15 and the 6, then I won't be able to do anything with the 10 and the 9. So it's better to use the 15 and the 9 together. So let's start by saying 15 and 9 can both be divided by 3. 15 divided by 3 is 5, and 9 divided by 3 is 3. Now let's work on the 10 and the 6. Both of these can be divided by 2. 10 divided by 2 is 5, and 6 divided by 2 is 3. And you could work on the p's at this point, but I say let's go ahead and regroup and see where we are now. So I've got 5 times p to the third times p to the second for the top. So that's going to make 25p to the fifth, because 3 plus 2 is 5. And I hope you recognize this is a place where we would need to use our product rule for exponents. Then in the denominator we have 3 times p squared times 3 times p, so that's going to be 9p to the third. Alright, now notice that I have more p's in the top than I do in the bottom. So when I say 5 minus 3, I'm going to get p squared, and that p squared needs to go in the top because that's where I have more p's. Now, ask yourself if 25 and 9 can both be divided by the same number. The answer is no, so these numbers don't need to simplify, but now we're just simplifying the variable. So it's going to be 25p squared over 9, and that's our final result for that part of the example. Now let's look at part B. So again, we have a division problem, and it needs to be written in multiplication form. Now to save on writing or typing if you're working in MyLabs Plus, what we're going to do is factor and convert to multiplication at the same time. So you know that when we convert to multiplication form, we leave the first fraction the same, we change divide to times, and we flip the second fraction. So we're going to be doing that as we go, but let's start with the top left, and let's just factor and copy as we go. So 3p squared plus 11p minus 4, that's a trinomial, and that's going to need to break down into two binomials. First times first is 3p squared. So that means we can put 3p times 1p here. The last term is negative, so that tells me the signs here need to be different. I don't know yet if it needs to be minus here and plus here or the other way around. Okay, the number is 4, so that tells me that the factors that go here are either 2 times 2 or 1 times 4. And I don't know, it might need to be 4 times 1. We just don't know until we put some numbers in there and see what we get for the middle term. So if I put the 1 here and the 4 here, I see that for the middle term, outer times outer is 12p and inner times inner is negative 1p. And that does happen to add up to positive 11p. So this factoring is right on the first try. Lucky us. And then in the denominator, notice we don't have a trinomial, but we have a binomial that has a GCF. So we can factor the GCF out of these two terms. 24 and 8 can both be divided by 8. And here we have p to the third and p squared, so that means that our GCF contains p squared. Okay, now in parentheses, 8p squared times 3p would make this first term, and 8p squared times 1 would make that second term. So that's how we got 3p minus 1. Now we're going to change divide to times, and we're going to flip this second fraction as we go. So what's in the bottom here, I'm actually going to write in the top. Look at these two terms. This is another binomial, very similar to the last one we worked on. And I see that my coefficients are 24 and 36. Now both of these numbers can be divided by 12. And I also see that my GCF needs to contain a p to the third. So our GCF here is going to be 12p to the third. And now inside the parentheses, 12p to the third times 2p would make this first term. And 12p to the third times 3 would make that second term. And then the denominator is this 9p plus 36, but notice it has a GCF. Both of these can be divided by 9. So if we factor out the 9, inside the parentheses we'll have p plus 4. Now let's look at the factors in the top and the factors in the bottom and see what can be canceled out. So I see that the top contains a 3p minus 1, and the bottom also contains a 3p minus 1, so those can go. And I see that the top contains a p plus 4, and so does the bottom, so those can go. Now let's also think about some of our coefficients here. I have a 12 in the top, and an 8 in the bottom, and also a 9 in the bottom. So 12 and 9 can both be divided by 3, but 12 and 8 can both be divided by 4. We're going to have to take care of both of those things, but we don't have to do them both in the same step. For this step, let's just start off by thinking about 12 and 9. So 12 and 9 can both be divided by 3, and that would leave 4 for the top and 3 for the bottom. And let's regroup at this point and just see where we are. So in the top, all that's left is 4p cubed times 2p minus 3. And in the bottom, what we have is 8 times p squared times 3. Now we know that 8 times 3 is 24, but I know I'm getting ready to reduce a little more, so I'm not even going to do that multiplying right now. Notice that 4 and 8 can both be divided by 4, and we're allowed to do that because 4 is definitely a factor of the top. It's 4 times the rest of that stuff, and 8 is a factor of the bottom. It's 8 times p squared times 3. So these are factors we can reduce with these. If we divide them both by 4, 4 divided by 4 is 1, and 8 divided by 4 is 2. Now think about the p's. Here we have p to the third in the top, and p to the second in the denominator. 3 minus 2 is 1, and the larger number of p's was in the top. So I'm going to end up with p to the first in the top. So that's going to be 1p times 2p minus 3. And in the bottom, we're going to have 2 times 3, which is 6. And remember, this p got canceled out from this p to the third in the top. That's how we got this p to the first power here. So this will not reduce any further, and that division is finished.